Okay, so the objectives of the end of this worksheet is to say I can draw a free body diagram to assist in discovering forces that are acting on the body, follow the directions, draw the free body diagram, label forces, solve the problems, always writing the equations first. All right, so Mrs. Nagel's mass is about 68 kilograms. There's me. I'm a little box today. Yeah, and now I'm going to have 68 kilograms. But then it's got to draw the forces. So, I could be standing on the floor or whatever. Oh, I'm sitting on the chair. So here's my chair. That was my chair. It's kind of a chair. It's a normal chair. It's not a big chair. All right, now it says I got to label forces. I have two forces. Force of gravity. Force of gravity. And what is my force of gravity? Well, force of gravity equals little g, my mass times gravity. Oh, how do I know that, Mrs. Nagel? Well, you come over here, the physics table, and there's this very lame equation. And I mean lame. Because if I multiply mass on both sides, mass cancels out, and then I get something useful. Force of gravity equals mass times gravity. That is a much better format. Okay, so that's what we're going to use. Force of gravity equals mg. And let's put that down. I can actually write it right here. It's going to be 68 kilograms times. Now you could put negative 9.8, but and that makes that pointing down, and that's the ultimate what we want. So, and that's what's like almost 70 times 10. So just a quick estimate, 70 times 10 will be like 700 newtons. You got to be less than that. Let's check. Put that in the calculator. 68 times 9.8. And you get the force of gravity is 660.4 newtons. All right. Now what? Well, what's the normal force that's pushing up on her? Well, her chair, technically it starts right here, but we usually do the center of mass. That's force normal. That's the force that's normally there that normal people never think about. Unless you're a physics student, then you can think about it. Now, what's a normal force? Oh, crap, I don't know what it. Well, it's not. It's balanced. So you're going to write the Fnet equals ma, but it's balanced. So there is no acceleration, so it's been 0 here. So Fnet equals 0. What are the two forces? Force normal is up, plus force of gravity, which points down, equals 0. Add force of gravity to both sides. Force normal equals force gravity. So we got 666.4. I hope you're not superstitious. And then force normal, 666.4. There you go. It's a lot of work for Mrs. Nagel. Yeah, you a physical person, probably difficult. A wonderful student. All right, hold on. I got to pause. All right, let's do the next one. A wonderful, smart student is standing up. What is the weight of the student in newtons? Because he has a mass. So we Oh, here's my student. Oh, I'm going to make it a little slimmer than me. Okay. 50 kilograms. Maybe I don't even want to write 50 kilograms in there. It's kind of makes it messy. What is the weight in students? What's weight? I don't remember. Well, force of gravity is weight. How do I know that? That's my handy dandy reference table. Booyah! Force of gravity, Fg. Weight or force due to gravity. Blah. There you go. That's how you know. What is that number? Over here. Right there. And I rearranged that to make it look useful. Yeah, I just got to put this stuff right here. So 50 kilograms times about almost 10. It's pointing down, so I want to use a negative 9.8 meters per second squared. Should be about 500. Let's check. 50 times 10. 50 times 9.8. 490 newtons. A kilogram meter per second squared is a newton. And it's pointing down, so just down the line. And what's the force normal? Well, hopefully by now, force normal, same. That force normal equals force of gravity. Why? I just did the same. I just did all that work up here. You can just say it. So, well, this one, by the way, is positive 480, positive. And I should put a negative up here. Oh, up there. Probably like, Mrs. Daigle, forgot your negative. I want 1,000 points. Equal and opposite. That way, when you add them up, you get 0 because it's not, you're not accelerating. All right, now I'm going to do spring constants. So I got to try to think of a spring, and I was like, like ball chair looks like a spring. Oh, sorry, I know that makes a lot of noise. So you guys want to know what a ball chair looks like? If you don't know, that's a ball chair. Can you see it? Yeah. So I sit on this all the time. There you go. Sit and smushes down. Okay. If you want to see what's I don't care about saying you. Get to the problem. I'm trying. All right, let's go. Oh, sorry. I wish I could delete all this fast, but I can't. Okay, let's see if that works better. I don't know if my pen might hit the camera. Whatever. A lovely, amazing physics student comes by and sits on Mrs. Nagel's ball chair. The ball has a spring constant, so the spring constant is 2,400 newtons divided by a meter. That's a unit. And it's compressed. That's your x. 30 centimeters. You've got to convert that to meters. Every number can be written over 1. Then you use this. There are 100 centimeters in 1 meter. When you multiply the numerators together, you get 30. You multiply the denominators together, you get 100. 30 divided by 100 is 0.3 meters. Now, what is the force acting on the spring? I'll drag it. I got to draw that with a free body diagram. Well, maybe I'll draw a ball this time. Oh, no. Well, it doesn't matter because I'm sitting on a ball. I'll draw myself a box. All right, and I'm sitting on a ball, so maybe I'll draw a spring, because that's my spring. And I have my spring constant pushing up and my force of gravity pushing down. It's kind of weird. I think I'm just going to make it look like this. Force of gravity, and then my force of the spring. This is the same effect. All right. Now, what is my force of this? What is the force acting on the spring? So it's trying to look for this. Fs. So I got to find the force of the spring. Well, get your handy dandy reference table out. Right there. Oh, goodness. It's so much, like if you're going to put this in this format, why not put that in this format? That's why I hate it. Just use that. Much easier. Force of the spring is Kx. So I can put 24,000 Newton meters. There's my K. Compression, notice I had to put it in meters. 0.3 meters. That way, meters cancel out. That's like meter over 1, right? No, it's like over 1. That's why I cancel that out. Multiply those together. 24 times 0.3. Oh, and what's my unit? That's Newton. That's a newton. Now, what is the weight of the student? Well, all right, let's do it's balanced. So here's some of the forces in the y-axis. Force net equals 0. I'm going to have my force of my spring plus a negative force of gravity equals 0. Add force of gravity on both sides. I'm left with force of the spring. No, that's the only thing on this side. Equals force of gravity. They're the same because it's balanced. Woo! So, you might want to use the signs because that would be helpful. 720 newtons. What is the weight of the student? Negative 720 newtons. Okay? I gotta pause. My dog's here. Pause. All right, it's getting later. All right. Spring, a lovely, amazing student comes by and sits in Mrs. Nagel's ball chair. The ball chair has another spring constant. So I have my student. I'm just going to make a quick diagram. The force of the spring, that's an S. Force of gravity. My force of the spring is Kx. My force of gravity is mg. And let's see what they're asking me. If the ball is compressed 5 centimeters, what is the force acting on the spring? Oh, I should rewrite that. Force acting on the spring. Let's look at the spring constant. Spring force. All right. So, all right. Force of the spring, Kx. I got my 3,000 Newton meters. I multiplied. Now I can't use 5 centimeters. I got to use 0.05 meters. How do I know? Take that number, divide by 100. It's not 5. It's not 0.5, it's 0.05. It's very tiny. Multiply them together. Bam, your answer. And the final answer is going to be in newtons. Because I can't tell. My dog is like, what's the weight of the student? The force of gravity equals the force of the spring. They're both equal to each other. Five. Now, what's going on? All right, I got a dog that's very antsy. Mrs. Nagel inflates more air into her ball, so that's going to make the spring constant change. A charming physics student whose mass is 65 kilograms comes by and sits on Mrs. Nagel's ball. Her ball is compressed 12 centimeters. What's the weight of the student newtons? Well, all right, first, force of gravity this way, force of the spring this way, this equation and that equation. What's the weight of the student? All right, well, we know that because mass is 65 kilograms. Gravity, negative 9.8 meters per second squared. Da-da-da. What's that? Almost 650. Stop it, dog. 65. Oops. Times 9.8. 637 newtons. Now, what is the weight of the student in newtons? We already know that. 637 newtons. Now, what is the spring constant of the newly air pumped? What? Well, we know. Okay, so you still know force net equals MA. Hopefully, you know this is 0 because it's not bouncing. You're going to say force of the spring equals force of gravity. They balance each other out. Now, I know one's going to be positive, one's going to be negative, but they're just directions. But the magnitude is the same. So, wait a minute. I'm trying to solve for K, and I know these. Well, I could put this and this equation in. I could put my equation for this, Kx, and I could substitute mg for this. I already know that Kx has to be equal to 3675 newtons because, I just did it over here. How do I solve for K? Well, I know my compression is 12 centimeters. My x is 0.12 meters. My k, I don't know. My mass, 65 kilograms. And my gravity is always 9.8 meters per second squared. And we're going to use negative because it's going to point down. But I'm not going to put negative here because I want to know it's pointing up, so it's positive. We're just going to look at it at the end. So I have to divide by x. What's my x? I'm running out of room here. My x is 12 centimeters. So divide by 12 meters. Divide by, 0.12 meters. So now the x and the 12 are the same. So now I have k. Where did I get my x? I got my x from here. Ugh, I just can't see it. Now my dog's mad at me. She's like, come on and play, Mom. It's 637 divided by 0.12, and then your answer is Newton meters. No fractions allowed. You can multiply that. All right, let's do the next one. There we go. Ugh. Miss Nagel inflates more air into a ball. Charming physics student has mass of 78. Going to do the same thing. Fg equals mg. Force of the spring equals kx. You can set the equations equal to each other. They are not accelerating. They are stationary. So I can say my force of my spring plus negative force of gravity equals 0. Subtract force of gravity from both sides. My force of my spring is equal to my force of gravity. I can substitute what I know for these numbers. Kx for the spring. Mg for this. So, where did I get this? From here. I don't know, is that clear? So now I have my really new equation is Kx equals mg. I want to know what the spring constant is. Put in my variables. Solving for k. I divide by x by both sides. K is equal to mass times gravity divided by the compression. Don't forget the compression of the chair is 8 centimeters. My x is 0.08 meters. My g is negative 9.8 meters per second squared. But remember, everything's going to be positive, so, you'll be okay. But maybe, negative here. And then x and my mass is 78. Plug that in, you'll get your final answer in Newton meters. That's what a spring constant is. Woo! Bye.